All right, so this is the Comp 9414 Artificial Intelligence course. This year, we're going to be having Comp 3411 students in the class for one-off. So can I get first an indication of who's enrolled in 9414, the postgrad course, and who's enrolled in the undergrad course? Okay, so a fair mix. Of course, there's a web stream as well, and this lecture theatre should be pretty much full because there's about 300 students in the course. There are going to be some changes to the course as it was. So we recently combined, 6 years ago, we combined the two AI courses together, undergrad and postgrad, but that never really worked as as desired because the two groups of students are quite different. So one of the things that's happening this term is that I'm rewriting the course. So you have to bear with me a little while the lectures are being prepared. So I've uploaded the slides for today, but I'll only be able to do that typically round about the time of the lecture. So we're also making a lot of changes in response to the new term structure, the 10-week term structure. One thing that this course does is have a 3-hour lecture. So I know it's a long time. I won't talk for 3 hours. I'll probably talk for 75 minutes and then have a break and then talk for another 75 at the most. So that's the sort of American-style way of doing things, except they don't have their two 75-minute lectures on the same day. But it does mean we'll be breaking up the material a little bit differently. The good side is you only have to come once for the lecture rather than twice a week. So hopefully we'll have a lot more time in between classes for the material to be learnt. And the other thing that we're doing with regards to terms is we used to teach a programming language called Prolog in this course. I used to teach this course about 6 or 7 years ago to postgrads. It takes about 4 or 5 weeks to even get anywhere up to speed with Prolog, and so we won't be doing Prolog because by the time we're up to 4 or 5 weeks, that's already the middle of term. So one of the major changes is to do Python. I should have introduced myself. I'm Wayne Wobke, and I'll be taking the lectures in this course. I will introduce the people in the course in a little while. So we're going to look at Python as a programming language. So hopefully, we haven't yet formally set that 9021, with the Programming Principles course, where Python is taught, is a prerequisite, but it will be soon. So we're assuming that you are familiar with and can program relatively well in Python. So if you are not able to do that, then you'll have to learn as you're going along. We won't use too many of the advanced features of Python, but we will use some of them. And I will talk about why Python is good. Python is good because Python's easy to write code in, easy to write but hard to debug, unfortunately. And Python is used quite a lot in AI, in industry particularly. Python has a lot of machine learning libraries that enable you to write lots of code in a very short amount of time, which is usually a good thing. So the two lectures today, the first bit's going to be sort of foundations, what is AI, and the second bit is going to be on agents. But the other thing I need to ask is, who's had the chance to read the course outline? I didn't think so. So I just want to say a little bit about some things in the course outline. Hang on. They've changed the resolution of everything around here, so it doesn't quite look the same for me. Maybe I'll set the resolution down here. Oh, no, that's way too much. Shall we go back to the old system? Every time, there's a story that every time Microsoft updates its products, the first thing everybody does is go back to the old settings. So that's what I'm doing right now. We'll see if it works. Yeah, a lot better. So one thing you could have done last week was set up Anaconda and Python. Has anybody used, in the 9021 students, did you use Anaconda last term? You did? Some people have, but did you use it last term? Okay, that's great. So, in terms of the course outline, I'm Wayne Wobke. We're going to have 4 tutors. I really encourage you to come to the tutorials. So, last term, tutorials were different. This is a totally new set of tutorials. So don't believe anything you've heard from friends about last term's tutorials or last term's course. It's going to be quite different. We've got 4 tutors, and all of them have an interest in applications of AI, which is something I'm particularly interested in as well. Alfred Schwitzky has worked with me for quite a number of years on developing various systems, and Caroline Gao was proudly showing me her video of her robot. That she worked for a company in Shenzhen. She's obviously from China. There's a lot of money in China and a lot of things happening in China, and particularly in Shenzhen. And she was showing me her little robot. And Anna is also working on social interaction with robots, so to speak, I think. So the tutorials are going to be 1 hour. We'll probably aim to have a sort of set of pen and paper exercises, but also some programming exercises. So hopefully every tutorial in which there isn't an assignment, there'll also be some Python programming, so you get to look at some actual code. We won't have a formal lab, though. We'll just have programming exercises. So a couple of new things. There is a forum, a class forum. In terms of posting queries, it's good to post general queries to the forum. The tutors are casual, so they can't really be expected to be answering questions all the time. So what I'm hoping to do is to have tutors, I'm supposed to not do that. Let's not bother logging in. I'll quit that. I'll log in with my own password a little later. So what's happening is, if any general inquiry, post to the forum. Don't email the tutors. If you've got a question of a personal nature, send the email direct to me. I'll talk about the lecture topics in a while. 10-week topics. The main point is there's no lecture next week. Next week is the Queen's birthday holiday, so there won't be a lecture on Monday next week. We will just skip that. And the other thing is there won't be a tutorial this week. So tutorials are going to start next week. So tutorials in week 2. So hopefully by the end of this week, we all know who's in the course, and there won't be any need to swap tutorials. And I would encourage everyone who hasn't chosen a tutorial to actually enroll in a tutorial, even if you don't intend to come, because we will need to mark your assignments. And so we'll need to know who's going to mark your assignments. So please do that as well. As I said, terms are confusing, so I had to write my own little calendar. And luckily, you don't have too much to remember in this course, because the assessment is going to be only there are 2 assignments and 1 exam at the end. So the 2 assignments we propose to have due in those weeks. So week 5 and week 9. And I should remind you about plagiarism. You shouldn't be plagiarizing. The course outline has the long blurb on plagiarism. Please read it. Don't submit other people's work as your own. So the course outline also has a list of Python resources as well that you can use if you are not up to speed with Python. Okay. So any questions so far about the outline or the structure? I'm going to say a bit more as we go along. Okay. Now, I don't usually do this, but I'm going to today. I'm going to say a little bit about me and why I'm teaching this course, and that might explain why we're going to do the things we're doing. So, funnily enough, has anyone here heard of deep learning? Some people think that deep learning is actually what AI is. I'm afraid I've lived long enough to see the world turn in a circle, and my first AI paper was on neural networks, which is deep learning. And I'm starting to hear the same words that I heard 30 years ago, along the lines of, we spent several hours trying to tweak this neural network, but we couldn't get it to work. Anyway, so we'll see how that goes. neural networks and deep learning are very fashionable today and indeed are doing some useful things. So we will not discuss that in this course. There's an entire course on deep learning that the school offers, and Alan Blair teaches that, so it's useful to do that. I've worked on logic and natural language. I've worked on knowledge representation and intelligent agents, which is the topic of the lecture today, and quite a few applications. So we did a desktop assistant where you talk in spoken language to your computer. We did a personal assistant on a PDA device that looks exactly like Siri, except it's before Siri because we didn't have the iPhone back then. And some applications in medical systems and some recommender systems. So if you actually go onto one of Australia's dating sites, you'll be using my software and Alfred's. And if you buy a new car on some of those sites, you'll be using our software as well. And so more recently, we've been looking at text mining, data mining applications for extraction of events. And I'm going to show you one of those systems later in the lecture and use that to motivate. So all of the topics that we discuss in the course today are directed towards sort of explaining how that system works and why it works. So the topic of the lecture today is, first of all, is what is artificial intelligence? And then just because AI is fairly popular nowadays, I used to do this at the end of the course. I'm going to do it now. What are some arguments against the possibility of AI that have been proposed? And then I'll show you that system that I talked about. So I have to begin by saying it's a bit unusual. A lot of people sort of ask me, what is AI? And sometimes I don't know if they expect an easy answer. There isn't an easy answer. It'll take me a little while to give some answers. But does anybody else come up with the same degree of scrutiny? I mean, does anyone ask, what is biology? Biology is the study of life. What's life? Oh, that's that thing with DNA. Okay, here's some DNA. Is that life? Is that alive? Is this bacterium alive? So AI seems to be subject to a certain degree of scrutiny or philosophical dispute, perhaps, that other disciplines are not. Anyway, we'll deal with that as we go along. So I didn't mention, but we are going to use this textbook by Poole and Mackworth. That textbook has the advantage of being freely available online, so hopefully you've been able to find it, just linked from the course webpage. And it's a very good book, easy to read, but it does have, it's sort of focused in one orientation, which is why, one reason we're using it. So this slide sort of answers the question, what is AI, by giving 8 different answers, and sort of the moral is, well, depends who you ask. And this is collected in the other textbook that we may refer to from time to time by Russell and Norvig. So these definitions are somewhat older, you might notice as well. So there's a kind of, well, AI is about trying to produce intelligence, but what does that really mean? We're going to have to come to answer that question in a little while as well. But there's a kind of thinking aspect to it, as in mental states, trying to model the mind. And there's a behavioral aspect, the action aspect. And cutting across that is the degree to which we care about whether we're modeling the mind of a person or human or not. So in one sense, we have to do it the way people do it, otherwise it's not really intelligent. And the other sense is, well, we don't really care what people do. People make mistakes all the time. Their reasoning is not really that good. We need to produce intelligent behavior. However, so looking particularly at some of these definitions, I don't know if they're very useful for you. Some of them talk about computational models, some of them talk about human thinking, some of them talk about decision making and problem solving, so they're trying to identify the type of activity that is regarded as requiring intelligence. And then some of them just talk about intelligent behavior generally, or intelligent agents generally, and there's a really big problem with all of these definitions because they presume that you know what intelligence is. So if artificial intelligence is supposed to be producing intelligence artificially, then we can't really make much progress until we know what intelligence is. So that's the first point. So my answer to the question is slightly similar. So I think there's 2 things going on. I think there's a scientific sort of objective, which is a hypothesis that intelligence, whatever that is computation, and we have to say what that is as well. And that is a scientific hypothesis in the sense that it could be wrong. So it's a bit like a hypothesis along the lines of life is DNA reproduction or something. It could be, or it might not be. And then there's an engineering angle to AI, which is, well, techniques for designing or building intelligent systems, yet we don't know what intelligence is yet. So the emphasis there is on, taking a particular problem or a constrained task and trying to build a system that accomplishes that task or works in some domain or achieves some particular purpose. And somehow the emphasis is not really on how people do that task or if people do that task, but what works, we have to define what works. And so it's an engineering discipline. That seems to be the view of the majority these days. So there's a kind of analogy between the flight of birds and the flight of aeroplanes. So the question that you might be posed is, the analogous question is, do aeroplanes actually fly? And on one answer to that, no, of course aeroplanes do not fly, because to fly you have to flap your wings. Aeroplanes don't do that, so clearly they're not flying. Or the other view, the engineering view, is, well, actually it didn't really matter. There's this general theory of aerodynamics. Birds satisfy it, planes satisfy it. Let's call flight anything that does that. So birds fly, aeroplanes fly as well. So maybe you don't care so much about these fine points, but we're going to make a few more of these fine points, quite a lot of them, I suppose, in the course of the lecture. And so the lesson here is that AI is perhaps to study or to look for those principles that underlie, this is the scientific part, underlie intelligence, whatever that is, in the aim that those principles are adopted or followed by people, as well as some of these software systems that we're trying to build. So unfortunately, the scientific hypothesis was something like intelligence is computation. But what is computation? So if we want to say, if it's going to have to be a hypothesis with some meat, then we need to say what the computation part is. So Alan Turing is going to play a prominent role in this lecture. Has everyone heard of Alan Turing in this room? I'm sure you have. I hope so. So Alan Turing is famous for several things, but one of the things he's famous for is the Church-Turing thesis, which defines a class of functions as being able to be computed, so computable functions. So I'm not going to give you the formal definition for Turing, because I don't need to, because we now today have programming languages that realize the Church-Turing thesis. So I can give to you the simpler answer, whatever Python can compute, that's a computable function. So part of Turing's argument is that that is as good a definition as any. You don't have to, whatever computable in Java is the same as whatever's computable in Python, whatever's computed in Prolog is the same as whatever's computed in Python, etc., etc. So basically anything you can write a computer program for, as you understand that term, that's computation. Well, if this is a scientific hypothesis, what isn't computation? So, well, brain processes. Now, back when I was writing my first paper on neural networks, that time people said, brain processes are not computation. I haven't heard anybody say that this time around, but maybe they'll get there. Geoffrey Hinton's still around. So it could well be that the processes in the brain, particularly those that do face or speech recognition, are not computations. That's something that people who study vision will want to determine. In fact, there's quite a well-known body of work where someone was actually able to show how the vision system of the brain actually worked in a computational sense, but of course it also had neurons and cones and rods and whatever it is in people's vision system. So you were able to describe the brain's operations in two ways. One way is in terms of the rods and the cones, and another way in terms of the computation. That is, of course, the Holy Grail, but nobody can do that for anything much other than vision, maybe hearing. certainly not for thought. So maybe brain processes are not computations. We don't know. What about evolutionary processes? Do evolutionary processes produce intelligence? Well, some people think so, but that's Darwinian natural selection, where, you know, survival of the fittest and all that. That doesn't necessarily require any computer to compute anything. And then there are these other people who think that complex adaptive systems underlie intelligence. So these are things like, well, maybe not ant colonies, I just threw that in there. Ant colonies seem to do things like create nests and mounds and all that, but doesn't necessarily require computation. And flocking birds. So I was going to actually show you the flocking birds video. Why not, since we've got it here? Just in case you don't know what I mean, this might actually try this one. So these are some birds. Oops. Oh, come on. That'll do us. So these little birds flying around, they seem to be producing intelligent behavior. Are they? Maybe they're not. Maybe they are. But they're not computing. Or are they? Well, they're certainly not computing as one big mass. We don't know what each individual bird's doing. There's been a lot of study of all of that. So is that intelligence or not? So if we're trying to delimit our field, we might want to say whether or not that's intelligence. Okay. So I said I'd talk about Turing. Anybody seen the movie, The Imitation Game? Of course, Benedict Cumberbatch is in that, but he's not Turing. And the movie is partly based upon Turing, but it's not fully based upon Turing. Turing's an interesting guy as well. In his personal life, I should tell you, being homosexual and probably having Asperger's syndrome meant that he had to play the imitation game quite a lot. But what is the imitation game? So in the imitation game, let's look at first this one called the Turing test. There's a human interrogator sitting behind a screen, and at the other side of the screen there's a human and an AI system. The human can ask questions and receive responses to both of the parties on the other side, and the aim is for the computer to imitate the human well enough to fool the human interrogator. If that is possible, then that's the Turing test. Can this interaction, which is only verbal in this case, can you fool a human interrogator? So the original imitation game, there's a man and a woman on the other side of the screen, and you have to work out which one is the male and which one is the female. In the Turing test, the other side of the screen is the human and the AI system. So Turing wrote a paper on this in 1950. So you'll see a lot of the work that's been done on this sort of question was done before there were real computers around to actually do it. So Turing's conclusion to this paper was, this question, can a machine think, is actually a meaningless question, a stupid question to ask. So don't bother asking that question. He actually says in the paper, in the future, we will speak of machines thinking without fearing being contradicted. And when he meant the future, he meant 50 years after he wrote the paper. So that's the year 2000 or thereabouts. Well, we don't think about machines thinking, but nevertheless, the conclusion still has some merit. Unfortunately, this is not really a test for intelligence either. So by that, I mean fooling someone is not really the aim of AI, so to speak. We don't really care about building a system that's going to somehow fool this interrogator into playing the game. Nevertheless, there is a prize called the Loebner Prize, $1 million or something if you actually pass this test. Or there was when I last taught this course. I haven't looked for a while. So some people think it's worthy of doing such a thing. So here's something as well that is an aim to, shall we say, fool the interrogator. So this is a system called ELIZA. And the user, ELIZA is meant to simulate a session with a therapist, by the way. The black, this is our dialogue. The black is what the user says. You can play with ELISA in the Powerhouse Museum. There's plenty of versions of this around. And the blue is what the computer says. So, yeah, men are all alike. In what way? They're always bugging us about something or other. Blah, 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 blah. Your boyfriend made you come here. He says, I'm depressed much of the time, etc., etc. So that's ELISA. If you look at this sentence, this carefully, and look at what the computer says, you'll see that the computer is not doing anything at all very sophisticated. So it's always pulling out stock phrases. Can you think of a specific example? Or repeating back what the user said. So the user said, my boyfriend made me come here. So the system says, your boyfriend made you come here. And then in doubt, when there's nothing more to say, it says, tell me more about your family. So, in fact, the point of ELISA is that there's no real intelligent behavior there at all, even though it might have fooled you for a little bit. It won't fool you for very long. So, the lesson there is you have to know how the thing works, or you have to look further. You can't just look at surface behavior. You have to know why or how this system is producing that behavior. And as I just said, it's a very simple rule-based thing. It doesn't have any memory at all, or maybe it maybe has a very simple sort of memory. It mainly spits back a version of what you said to it in the first place. So many more and more sophisticated systems are trying to do things like that and win that Loebner Prize by fooling the interrogator. So here's another. So that doesn't really wash. It's got to be, I think my lesson is there's got to be a little bit more than behavior to determine whether something's intelligent there. And fooling the everyday user on the street maybe isn't enough. So another famous system is called Schödlu. This has slightly different problems. Schödlu operates in this sort of blocks world. So the blocks world is, as we see, there's a table and there's a bunch of blocks on it. And so you can only talk about things in this blocks world. There's a very famous PhD thesis, and there's some dialogue in here. And in this case, the user can issue commands, though the system doesn't really do much other than respond to those commands. And the system responds not by actually moving any blocks. It's all simulated, so it'll pick up and sort of just on its graphics monitor move the blocks around. So this particular one goes, pick up a big red block, find a block which is taller than the one you're holding and put it into the box. Now, this is all typed. There's no speech recognition going on here. That looks like a very complex expression for somebody to understand. First lesson, for a computer, a phrase like a block which is taller than the one you are holding is actually very easy. So it's got a standard syntactical structure. That's easy for a computer to process, even though it might be hard for a person. What does the box contain? The blue pyramid and the blue block. So there's a bit of cleverness in how the referring expressions are generated. So it refers to the blue pyramid and not just the pyramid, and so on. What's the pyramid? Supported by the box. So this system, as I said, was pretty well known, but it is a mess. So if you look at what underlying theory there isn't one. If you look at how these sentences are generated, it's just one massive program. So it's not really clear how general this is. And the other problem with it is it only works in the blocks world. So this really can't scale. It can't be a general principle. It can't be something that you could extend to other domains very easily. So the problem here is we're talking about these micro worlds. You only can talk about blocks. You can't move outside that micro world in this case. Also, there's a replicability problem we don't really know, because this software is so complex it doesn't really run anymore, although some people have tried. You can't really test it out to see how well it performs when there are different configurations of blocks and so on. So this is a well-known system as well, but is it any better? My question is, it's different. Is it any better than the ELISA system or the variants of ELISA to pass the Turing test? So behavior is probably not enough to identify intelligence. So the alternative view is, an alternative view is proposed by Newell and Simon. So Newell's the psychologist and Simon's the economist at Carnegie Mellon University. The claim is, this is a different kind of claim, that AI requires a physical symbol system. So what is computing? Well, it's symbols in the brain or something like that. So a symbol is some kind of pattern. Think of a symbol as like a word or a number that you can manipulate, and you manipulate symbols by combining them into other symbols. So the claim is that actually you need such a complex system or a symbol system, not one of those flocking birds type things, but a symbol system to implement general intelligent action. That's the exact wording of Newell and Simon. And, you know, one of the critiques that I'll come to later talks about, well, does the system really know what a blue pyramid is? It's only a thing in a memory. For Newell and Simon, it's a bit more than just a bunch of symbols. It's an expression designates an object if the expression can either affect the object or behave in ways dependent on the object. So they're trying to say it's not just enough to have a symbol system, but that symbol system, well, a symbol system is not enough in isolation. The symbol system does, in fact, exist in the world. So we're starting to move from disembodied intelligence to robotics, where there's a robot that has a presence in the world and has to affect real things in the world, like real pyramids. Don't worry too much if you're not following all of these points, because these things are quite complicated. So, in fact, after the early days of AI, where all of these things were tried and nothing really worked satisfactorily, a scientific approach was adopted. So I'm sort of giving this in a historical way as well, this lecture. And if you look at the antecedents of AI, there are lots and lots and lots of them. And that's why there can be lots and lots of AI courses. And the AI course that I'm going to take draws on some of these strands going through these people, this work. And the course that Adam Blair used to do followed a slightly different strand through this work. So most people will say that this symbolic systems approach goes right back to Aristotle, 350 BC. Aristotle has a formal logic, so a system where you can reason about sentences. So his example was, all men are mortal, Socrates is a man, therefore Socrates is immortal, and you can reason about that using symbols without knowing who Socrates is and without knowing what mortality is. So that's a key point, that it's a formal reasoning. It's not just you had to understand that there was a formality involved. And that, nothing much happened in logic until the Middle Ages, and then even till Boole with the Boolean algebra. So if you've seen your Boolean expressions involving ands and or, then that's George Boole's work from that period. Then Frege and Tarski built upon that. So a lot of this work sort of happened in the early part of the 20th century. Of course, there are formal algorithms, and the oldest known algorithm is Euclid's algorithm for whatever it is, lowest common divisor or something, highest common divisor. And then you've got probability theory. So there's a whole strand in terms of reasoning with uncertainty. So probability theory, utility theory comes from utilitarianism, and that work combined with probability. So there's this probability decision theory, so decision theory according to Bellman. So all of that sort of work takes AI as a kind of reasoning with uncertainty or probabilistic reasoning. So if you look at Russell and Norvik's textbook, Stuart Russell works on that area, so it's very good on uncertainty, statistical reasoning, game theory and such like, and decision theory. But that's not the strand I'm taking. We will talk about probabilistic reasoning, but not to the degree that they do. So some of these other strands include dynamical systems. I don't think anyone really works on dynamical systems, but it is a kind of antecedent of some of the works on cybernetics and control theory. So those guys were trying to build very simple mechanisms, the precursors of robots, I would say. Neural networks, as I said before, wasn't new when I did it in 1986. The main work on neural networks comes from McCulloch and Pitts, 1940s. I'm going to talk about some of their work later on. Logic work continued with Gödel and Turing himself, so that's the other side of Turing, another aspect of Turing's work. And even structural linguistics, I think, should get a mention in here, trying to define a discipline called linguistics. And that's still, I think some of those distinctions are made today. And so we still sort of finish with, in this list, with Chomsky in 1957 talking about formal linguistics and grammar and natural language processing. So there's a whole strand of computational linguistics that follows through that strand. So now we have gone from writing a few simple systems that don't work too well to having too much to draw upon. So, you know, no one knows everything there is to know about all of these topics. And building an AI system, potentially, well, if it's going to be one of human-level performance, it's going to have to outperform and draw upon all of those things. So I guess at this point it's as good as any to ask, who thinks there's going to be human-level AI performance anytime soon? Alan says he used to ask that question in his first class tutorial. I'm here to tell you that's probably not going to happen anytime soon. And I went to a workshop in the arts faculty where they'd seemed to devote a whole morning to discussing the time when robots were going to take over the world. And that isn't going to happen anytime soon. So AI is actually big, complex, and theorizing about AI requires lots of background. So if you're going to do it properly, I suggest a lot of background reading is required. So not only are these historical antecedents, but there's related disciplines. So much of the work in AI draws upon philosophy to a degree. I mean, not really directly, but if we're going to talk about an AI system as knowing something, then we ought to look at philosophy of knowledge, perhaps. Or if we're going to think about the relationship between a computer and a robot, then we ought to look at the mind-body problem. And if we're going to make a scientific claim that intelligence is computation, we ought to look at what that claim really means, what that amounts to. So nothing's so straightforward. Then we've got psychology. Psychology is quite interesting in that back in the older days, there was a much more of a tight integration between computer science and psychology. But I don't know if that's still the case anymore. But the real problem is, if you've been following the literature, there's a replicability crisis. So what that means is a lot of the classic experiments in psychology can't be replicated. So they're now saying, well, maybe we don't actually know very much about human psychology, as much as we thought. So when we AI people want to talk to cognitive psychologists, you're looking for big ideas or the structure of the brain or how memory works, but they don't really have much to say about those sorts of models. So the models typically are there for very specific purposes. There's neuroscience as well, so you can take pictures of the brain and it'll say, well, this bit seems to be a bit more active when you're reading and this bit's a bit more active in other times. But that's about as far as it goes. So given that we've got 100 billion neurons in our brains, give or take a few billion, then and each one of those has up to 10,000 connections, then we have 100 billion times 10,000 things to think about. Is it any wonder that neuroscientists don't really know that much about how the brain works? So we really need to know, which bits of the brain, what are they doing, how are they connected? No one really knows. So I missed out linguistics. So there's a strand of linguistics that talks about language processing, parsing. I'll talk about that later in the lecture. These days, computational linguistics is almost the same as a statistical learning. So most of the papers you'll read rely upon statistics, the corpus-based, the old-fashioned, the 30s style approach, using statistics and learning. So there's these other things to draw upon, but it's a little more difficult than it used to be. And I've got to mention science fiction. I begin to wonder, because there's some of our talks at UNSW, they say things like, well, these tech gurus are really worried about AI. Well, are they? Why? I wonder if they've been reading a little too much science fiction. So, again, in Western culture, science fiction goes, robots and producing intelligence goes back a very long way to the Pygmalion myth and Talos in Greek mythology, and then you've got some of these other ones. So everyone knows Frankenstein's monster, everybody knows Carol Capek's robots, everybody knows Asimov's 3 laws of robotics, and so on. I don't know Astro Boy because that's Japanese. I never really saw that. But my point is that this is not science. So don't be fooled by what the tech gurus say or by what the robots are coming to get you kind of approach. You're going to create a monster that's going to eat you up kind of approach. That isn't going to happen anytime soon. And I wonder, this is Alan's slide as well, good or evil? Robots, good or evil? So Astro Boy is apparently a good robot. I begin to wonder if in Japan their positive attitude towards robots, apparently so, derives partly from this cultural difference in their, they don't have the Terminator robot that we have here, the one that takes over people. So, and my point is, are robots good or evil is a stupid question. Presumably this is one of these Turing type, we shouldn't ask that question. It's not worth asking. Maybe it references the Google don't do evil kind of thing as well. That's a deliberate choice of word there. But our point is, there's not going to be a yes-no answer to that question. There's going to be things about robots and robotics that will influence the world as you are getting older, as I am as well, and there will be bad things as well. And they might come together. So there's not going to be an easy, oh yes, robots are bad, we've got to ban them entirely. Robots are good, well, we just do whatever we feel like. In fact, there's much more to it. So some of the things, for example, that are of pressing concern are things like autonomous weapons systems, which are capable of essentially killing machines or killing robots, a bit more like the Terminator. And what conditions under which those things ought to be allowed to operate or to be regulated or somehow controlled. Anyway, so that's, I'm not sure if this is the right time, but that's the sort of there's a bit of a historical overview on where we're at. But I'm going to also talk about why there can possibly not be AI. Are there arguments against AI? So first, sort of type of argument, I'm not going to talk about it until later on in the lecture, which is one by Brooks. Basically, the argument is, well, you're focusing too much on the computer, you're not focusing on the body, the robot. So Brooks is very interested in building machines that operate, for example, on the surface of Mars that don't really have any sophisticated intelligence. Probably don't need necessarily that on the surface of Mars, but are capable of survival. The three, I won't say much about Pinker, how the mind works. I'm not sure if there's, as I said before, some real specific enough knowledge on that. Some of the philosophical objections I will talk about, though, because they're sort of amusing. One of them is based on a fancy theorem. Turing again, by the way, I didn't put it down. One based on a so-called Chinese room, and one based on Dreyfus's analysis of skills. So before we even get there, there's the classic argument against AI, which is not necessarily an argument, but I'm going to call it the X factor just because I felt like it. A computer can't be intelligent because it can't do this. It can't do any one of those things. So it can't be creative or generate insights. Can't produce poetry or write a symphony or draw a work of art. Can't beat the world champion of chess or Go. Can't make mistakes. Someone said that one to me recently. Can't have emotions or empathy. Can't be conscious. Doesn't have free will. Doesn't possess the vital spirit or a soul. And another big one, doesn't have qualia, as in can't experience things. Now, people can experience things like the taste of ice cream, but your average robot probably can't do that. So I'm calling that the argument, not really an argument, but the X factor. So there's a kind of, well, yeah, you can build these robots and build these systems, but they're not really intelligent because they don't have X, where X is all of these things, or one of these things. By the way, the computer can beat the world champion of chess and Go now. So that's one that we can tick off the list. So that's just kind of the lesson as well, that sometimes you can start ticking things off the list. Not all of them, but anything that looks behavioral or functional, you can tick that off the list sometimes, and then, oh, well, what do you say? Well, actually, that meant that playing chess didn't require intelligence. Chess was actually easier than we thought. Or is the machine intelligent? So typically, we say the latter. No, the former. We say that chess is actually easier than we thought. Go is actually easier than we thought. The World Championship match was pretty interesting, the match with the Go champion. The World Champion defeated the computer once, and once only, by making a move that no one had ever seen before. So even when you watch the movie, the experts around there sort of flummoxed, like, they just ignored the move. It was a classical thing. So the experts couldn't understand why the world champion made this move, and they just didn't talk about it at all. They're talking about a different part of the board. And yet that's the only case where the human won. So this particular Go playing computer is one that Google DeepMind built. And it works in a classic style, but it has an awful lot of hardware. So you see the movie and they're bringing in all their computers, tons of them, and a massive amount of computation going on behind the scenes to just make one move. Nevertheless, it won the match. Therefore, Go couldn't have been as complicated as we thought. Now, I don't know if people actually apply this argument in the following way, but has anyone here actually written a symphony lately? In such a case, does that mean that you're not intelligent? Because after all, you can't be intelligent unless you can write a symphony, can you? According to this X factor argument. So it's sort of one computer against the entirety of the world. Unless you're Mozart, forget it. So there's a kind of, upping the ante here. And we don't really care. I mean, it's not really necessarily objective. There's more mundane things that are complicated enough. The classic one, maybe I didn't write it up, is can't produce anything that hasn't been programmed. That's the usual way of expressing that. So another one is by Searle. So this kind of argument, why can't there be AI? Well, let's distinguish first of all, and maybe this is wrong, but this claim of weak AI, that we can build intelligent machines, robots, whatnot, but that's only a tool to study the mind. It doesn't really have intelligence, it only simulates intelligence. And then there's this strong AI claim that this is all that's required for intelligence, like the physical symbol system hypothesis. You build a robot, it actually has a mind, it has cognitive states, it understands language, not just pretends to. We'll come to that one in a minute, this weak versus strong thing. So let me just say a little about some of these are funny arguments. You can sit back and relax now. So there's a famous theorem called the incompleteness theorem. And any formal system, any computer program, well, there's going to be a sentence that program cannot actually prove, even though it seems to be true. And this sentence, I won't tell you what it is, but it's rather a sentence like G cannot be proven. So the sentence G is G cannot be proven. Now, of course, any consistent system can't prove that. If it proves it, then it's saying that G can't be proven, so it's inconsistent. So it's a bit like one of these liar paradoxes. If I say this sentence is false, that sentence can't be true and it can't be false either. So someone's sort of taken this, well, somehow that means that your computer cannot be intelligent because people can easily see the truth of such sentences. Now, I don't know how easily you can see that, but it takes people quite a while to get their heads around these liar paradoxes, and the Gödel's paradoxes are even more so. And if I actually write out this computer program, is probably going to be very long, and the Gödel sentence is probably going to have several million words in it, or maybe even more. So is it really that you could easily see that that is true, that particular sentence of this particular system, if this was a representation of your own system? So this is not really a good argument against AI, but nevertheless, you'll see people pulling it out. They'll say, oh, but Gödel showed that no system can prove everything that's true in that system. Yep, that's right, but so what? And then there's the Chinese room. So that won't work. This example won't work for you if you come from China. So you can call it the Hungarian room or something. So let's call it the Hungarian room. So Searle's argument for the weak and the strong AI is something like this. We pretend there's a room, and instead of a computer, the room is going to implement the program by pen by paper. So the human is going to act the role of the CPU and transfer information from bits of paper, a bit like the way that a real computer, uses RAM, memory. So Searle says, okay, the human doesn't understand Hungarian. The human's just passing these bits of paper to and fro. The human's analogous to the computer program, and that means the computer program doesn't understand doesn't understand Hungarian, the language, because all the human's doing is manipulating these symbols. That's the symbol hypothesis again. So manipulating symbols is what the human's doing. Human just doesn't know what's on these symbols, can't understand the symbols. Human's analogous to the program, therefore the program doesn't understand language, and therefore that AI doesn't either. Well, one way to approach that is to say, why do we have to work out where the understanding is? So this is a complex system. It's got a computer, it's got a memory, it's got connectors to the world maybe. If you do the same to your brain, if I cut up your brain, cut your head open, poke around in there a bit, where's the understanding? And why do I have to be able to say where it is? Which neurons are doing the understanding? And which ones aren't? So it's not quite so simple to make this analogy as to, well, the computer's just like the human in the room who moves pieces of paper around. So this argument sort of doesn't work, but there's some merit to this as well, because what arose from this is this idea that we need to look at how symbols acquire meaning, or how symbols acquire meaning for the agent. So this argument sort of pushes you in that direction, but doesn't quite get it right, I don't think. Okay, here's a fun one, so don't really take this one too seriously, although I wonder if sometimes people do take this one seriously. Well, what would happen if you took your brain and took out every neuron one at a time and put an electronic transistor in there instead? Well, the point is the behavior of the system would be the same, exactly the same. That's by definition. But presumably one's consciousness disappears, according to Searle. Or, if you're this other guy, Moravec, robotics researcher, you get a conscious machine. I have no idea what you get. But sometimes, what should we say here? Should we say this is a stupid question because we can't really do that? Or we don't really know what would happen even if you could do that. But it does rather look at this X factor thing again. So do you need to be conscious or not? So does it mean that you gradually lost your understanding when we did this, in which case your consciousness was important for your intelligence? Or does it mean, actually, no, consciousness doesn't really matter. It's something we have, for sure, but it's not really intrinsic to our intelligence. We don't know the answer to that. So there are plenty of people who study or try to study consciousness, but some of them are a bit strange. I mean, there are Santa Fe Institute and places like that, and you wonder whether they are really addressing the core problem. So this is a mystery. I think we just have to say nobody really knows what consciousness is. Consciousness, even if studied scientifically, we still don't know what the answer to the core question. Anyway, the point here was that Searle, the strong AI, weak AI person, thinks that because you would gradually lose consciousness here, you would not be intelligent either. Therefore, no brain, no computer or robot could be intelligent. Anyway, so all of that's a bit of speculation, a bit of fun maybe. Read that when you want to. Don't worry too much. It's not going to be assessed in this course anyway. But we sort of now go back to, well, I think the short version for me is nobody's really shown AI isn't possible, and nobody's really shown it is possible. That's why we have a scientific hypothesis. Let's look at the practice. So there's state of the art coming later, but state of the practice coming now. Which of the following can be done right now? So have a look at those things on the list. And these are tasks. They're not quite as narrowly defined as manipulating blocks in the blocks world, but they're pretty interesting sorts of tasks. Now, they're not general intelligence either. So probably the state of the practice is that some of these are possible now and some of them are not. I actually don't know which are which because I didn't bother checking. It doesn't really matter. But we do know that, definitely AI systems can play games like chess and Go, bridge and poker, but those games are narrowly constrained as well. Can AI prove a mathematical theorem? I don't know. Depends maybe what you meant by a new mathematical theorem. So these are where there's sort of engineering work trying to be done, trying to improve performance or even get any sort of performance in some of these scenarios that are more general, as I said, than the micro worlds, but they're not by any means human-level intelligence across the board. There's another historical point. This is Alan's point as well. Apparently, I think this must be from that Space Odyssey movie. Chess or vision? Which is easier? Who's going to vote for chess being easier? Who's going to vote for vision being easier? Nobody voted much. That's normal. Back in the old days, when this movie was made, 1968, people thought that chess was hard and vision was easy. Nowadays, it's the complete opposite. Chess is easy, vision is really hard. So vision is hard because partly we don't know how to do it. People can recognize faces in very short space of time, but don't actually know how. Saying we've got a big neural network in there only doesn't really tell us how it works. And yet chess is something that's easier because typically you can assume that the game rules are well defined and do not change. So it's a constrained problem. There's only so many moves you can make. There's only so big the game tree can be. You don't have to worry, and the computer doesn't even have to worry about moving the pieces. It would be a whole bit different game if the robot actually had to pick up the piece and move it. But even that doesn't happen. So chess is a sort of domain or problem that can be easily characterized. Doesn't mean it's easy to solve that problem, but it's easy to specify what it actually is. Whereas vision, it's not even clear. I mean, how do we recognize that's a chair or this is a desk, or how do we walk across the room avoiding obstacles? It's very hard to actually do that. So in fact, vision is much harder, much harder than chess. So some of the recent advances, I don't know how recent this is, there's certainly industrial robots doing lots of interesting but constrained things. So loading and unloading ships. So if you go down to the docks, most of that is now, most of the unloading and loading of containers and also the scheduling of all of that, because it's not that easy to take them all off and put the different ones on. All of that can be done automatically. You've got little robots zipping around warehouses, think Amazon. I don't know if they quite have robots in all their places, but your robot zips around, gets the item, takes it back to the desk and says, here, this is the thing that they ordered. That's quite common. They have lots of little racks, so I've seen a video of this. So rack sort of going around the warehouse, and robots have to avoid running into each other is the main problem there. And of course, self-driving cars. So self-driving cars is a latest thing. This one may be slightly more complicated because the domain, or when everything, let's put it like this, when everything works well, so your self-driving car will be okay. When everything does not work so well, when things go wrong, then we might have a problem. So there have been some accidents with self-driving cars. Typically it's where it's a very dark road and a cyclist just appears in the middle of a highway, or you're driving along a road and you see a white truck and it's sunlight right behind the white truck, so the kind of scenario where a human would also not see so clearly, but the driverless car had the accident. So there are several cases there where I think there's a question. So there are technologies and there are systems there that will perform some task reasonably adequately, but will lack that fine judgment, perhaps. So here am I using the X factor fine judgment that humans might have in that scenario. So that's definitely happening. And some of the other areas, of course, deep learning is very popular these days and has achieved quite good results, so it would seem, on image classification, less so on language processing, but game playing. So the game playing AlphaGo system that I referred to earlier that beat the world champion in Go, that system is one that uses a neural, I think, we don't know because Google didn't say, but it uses a neural network to decide either which path to search or which policy to pursue. I'm not sure exactly how, but there's a neural network in there somewhere. Now, another one which is now sort of less recent, but recent, still slightly more recent, there's this massive thing called Watson. IBM sort of marketing department loves Watson, but nobody quite knows what Watson is when they're talking about it. But there is if you know the American show Jeopardy, there's a game show where I think that Watson has to propose the question or something to which the answer is already given. Anyway, Watson tries to do a lot, to bring a lot of technologies together, and that's how it uses a lot of traditional technologies to essentially keyword matching on a very large encyclopedia, ranking options. So it does a lot of stuff. Now, we don't necessarily want to say that Watson is intelligent. We're just saying, I'm pointing out, well, how does that differ from those earlier systems? So it's more complex, but it's not. But is it doing anything particularly sophisticated? Maybe, or not. So I'm nearly at the end of the first lecture. So what I was going to do is show you the system that Alfred basically wrote. I can't claim too much credit for this one. And as a kind of AI system where we perform a fairly narrow task, but it's got a whole bunch of technologies in it. So this is, I'll explain it as it was. And I think this is something that's happening in AI as well, which is, you're not just building one standalone system anymore. You're building a system that relies upon lots and lots of other pieces of technology, and you're sort of making, a bit like Watson, you're building a much more complex system. So this is a system that we did for event extraction for Afghanistan. So the idea was the user is some kind of analyst who needs to track the war effort in Afghanistan, and they need to monitor these news sources, and they need to say, is there any event happening in this news source that is something I should take note of? And I need to store that event so that later I can see if I can backtrack and search and find what events occurred before. So this is a big trend in AI that I probably should have put on the slide. Because, in Alan's strand, there isn't so much here, but there's so much work done on text mining. So anyone wants a job in text mining, no problems. My former researcher now works for Commonwealth Bank doing text mining. There's just so much text around here to process. So it's not all happening in vision and games, it's text mining as well. So in this particular case, we have a fairly complex pipeline. It sucks in newspaper articles online from 20 or so foreign but English language websites and splits them up into sentences, works out the part of speech of the words in that sentence using standard technology, does a syntactic structure. So down here is the structure of that sentence. We'll have to talk about that later in the class, but it divides the sentence up into phrases and does that in an automated fashion. That's free, open source software. And then we have another system over here that we want to determine the actors and the targets and the action in this event. So this one's actually wrong, deliberately so. So I'm going to remove that. And I'm going to click that one and make that the action. So this, oops, that was supposed to be, I clicked it twice, so that's why it didn't work. And then over here, there's an ontology. So an ontology is a knowledge structure that lists a whole bunch of events that they're interested in, a whole bunch of actors who could be doing those events, and a whole bunch of other things as well. So prominent in there is killing. The most common event is killing, by the way. I'm afraid this is a war after all. There are different types of killing. I never knew about donkey-borne IEDs until I started this project, but that's pretty important as well. So you put the bomb on the donkey. Anyhow, so after all this, if we save this rule, you actually learn the pattern, and next time around this same sentence occurs, this rule will actually be applied and will automatically extract the sentence, the event for you. So this typical system has so many components, and I was reflecting before today that we couldn't actually have built this system 10 years ago. So 10 years ago, you probably could have done some of this. So there was, part of speech tagging was probably done to reasonably high level of accuracy, but it's probably better these days. Parsing wouldn't have worked. It would have crashed all the time. I've never seen this particular parser crash. It doesn't always work correctly, but it does never crash. I've never seen it crash. And it's a system where we need a lot of user expertise. So all of this stuff in the ontology comes from a domain expert who tells us you need to look at the donkeys, or you need to look at, these particular people are important, this particular area is important, these events are important. So it is constrained, but it's quite general. There's about 1,300 things in here. So it's a massive amount of effort to do that and to extract events that have that. So this, and there's learning in there as well. So there's inductive learning to try to infer generalized rules from the user's input. So this is a kind of trend, I think, of a more complex AI type system. The details don't matter. So I've just said what's on that slide. And so what that does is motivate the topics in some ways. By the end of the semester, you'll understand how to build that system, but it will take the whole semester. So we're going to have to look at, well, some fundamental issues in AI, including search. So every AI course has got to talk about search because, the idea is that, solutions have to be found by search. Constraint satisfaction is a very important technique as well. And the authors of the textbook, Mackworth is well known for his work on constraint satisfaction. We need logic and knowledge representation to represent that ontology, and that will also be discussed in week 9 with the knowledge-based systems. And natural language processing and machine learning tie in there as well in weeks 7 and 8. And uncertainty, although there's no explicit uncertainty in that system, there is in the part of speech tagging, and there is in the parsing. So there's a lot of underlying technologies there that have been put together and that we've sort of linked them all together and thrown in some learning and thrown in some ontology to get it to work. I won't say too much. I do want to say something about neural networks and reinforcement learning, but that's not going to be the prime part of my course here. So there's a whole lot of stuff we're not covering in this particular course, And so those are things like robotics. That's too hard if you need the differential equations for that, and same with vision. I'm not going to do statistical learning. There's a course on machine learning that Mike Bain offers, a course above, beyond that on statistical learning. There's a course on deep learning here at UNSW. I'm not going to talk about game playing much because there's other things to do. Evolutionary algorithms I won't talk about, multi-agent systems or recommender systems or dialogue systems. So I'm leaving an awful lot out, as one must in any AI course. So I've sort of come to the end of Lecture 1A. So what I'm saying, I think the state of the art is in some ways promising, more promising for the engineering than it is for the science. So there seem to be some quite recent advances on some of these sub-problems. Many of those advances, although I didn't say so, rely upon the use of large data sets for training, and some models make use of human expertise and learning. So there's not necessarily a sense of the machine's going to do it all, but the machine's going to need some human input. And I see a trend towards more complex software development, so software systems. It's where Python comes in as well. It's not just going to be a one little AI system, but it's a huge software engineering effort as well. In terms of the science, however, I think the story is a bit more pessimistic. I don't think there's anything anywhere close to some general theory of intelligence floating around. In many domains, I don't think you'll get close to human reasoning, and I don't think anyone really knows how the brain works in detail, in sufficient detail for us. Anyway, that's enough for one lecture. I'm still not done with some of the conceptual stuff. In the second lecture, we're going to talk about agents. Maybe I'll just leave it for the second lecture. So we'll have a little break, shall we? So why don't we wait for 15 minutes or so, and I'll come back and we'll start Lecture 1B. First up this term. So for that reason alone, I'd like to finish a little early. But we'll see how we go. So this lecture is about agents. I mentioned before that I do research on agents, so I have to make sure I get it right. The textbooks, unfortunately, don't get it right. So what I'm going to say is a lot more than what both Russell and Norvig say in their textbook and what Poole and Mackworth say in their textbook. So Poole and Mackworth say blithely, well, AI is about building agents. Well, that's not 100% right anyway, because when we look at some of those applications for search next week, they won't be agent applications. They'll be standalone non-agent applications. We'll see what we mean by that anyway. So the purpose of the lecture is to say what agents are, and indeed, thinking about an AI system as an agent does have its advantages, and designing an AI system as an agent does have its advantages as well. And importantly, agent architectures are very useful for building efficient systems and thinking about complexity and, more importantly, embeddedness in the world. So this is where the computer meets the robots. And we'll talk about agent programs and look at the particular example. This is from the Poole and Mackworth book on the delivery robots, because this they use as a very nice example of how to define an agent architecture and build an agent program for a simple task. So that's a more concrete example. I don't think they actually built the robot. Maybe they did. And then I'll talk about so-called rational agents. Now, when we say agency, of course, this is yet another one of those terms like intelligence that could mean several things. And even if you look at a standard dictionary, there are 3 different meanings for the term agent. And we typically mean the first definition here, the agent as the actor, the entity, the thing that does something. It acts, and it acts autonomously, and it acts in the world, and it's got goals. It achieves goals. And the agent may or may not be rational. So we're drawing upon this tradition of rationality as well. The agent may have beliefs or desires and intentions. So there's a class of agents, the BDI, belief, desire, intention agents, that we'll talk about also. So agents can be simple, agents can be complicated, but they all act in the world. That's one sense of agency. The other sense is the agent that you have when you go to your travel agent or your real estate agent, those are the agents that help or represent you. So they're helping you do something and representing you on behalf of, they're representing on your behalf to perform some task. So the real estate agent's going to sell your home for you. And the system that I showed you before was such an agent. It collaborates with the user on some presumably complex task. So it may or may not be an agent as the actor. And then there's the third sense of agency, which is one we not even care about in this course, where we say, oh, the agent of this thing was oxygen, the cause of a chemical reaction. So unfortunately, the textbooks don't really distinguish those first two things. They just call them all agents and then say AI is about agents. Well, is it about the first sort or the second sort or both? And if you look at the examples of Poole and Mackworth, then they're actually, in some cases, the second sort, and in some cases, the first sort. But when they do give an example of an agent as a helper, it tends to be one where it also is an agent of the first sort, if that makes sense. So what's an agent according to one's intuition? So some entity that is essentially connected to some environment. So the agent's in the world, this environment, it doesn't see the whole world, the whole universe, just the bits that it can see, and it has sensors, and it acts through effectors or actuators. So essentially a robot with a limited sensory system. So the human agent has various sensors, eyes, ears, and touch, etc. And the robotic agent has something similar but different. So the agent, now what is an agent? Unfortunately, for Poole and Mackworth, let's have a look at I've tried to draw these in order. So this is according to Poole and Mackworth. Well, okay, so person is an agent, robot is an agent, dog is an agent, worm is an agent, lamp is an agent, computer program that buys and sells, or a corporation. Now I'm going to say that's not quite right. So insofar as the agent acts or has goals or operates according to goals, your lamp doesn't actually do it. A lamp merely turns on and off when you click the switch. So lamp, not really an agent. What about a corporation? Can a corporation have goals? Well, a corporation's a set of individuals. Corporations can hire people and fire people, so they can do things, but not so clear to me that that's a single agent. And what about a worm? So how are we going to make sense of all that? Or a dog? I'll talk about my dog in a minute. So an agent, here's the more official definition that agent researchers use. And we'll underline the importance of each one of these things as we go along. So situatedness is the most important thing. So the agent operates in a dynamically changing environment. The agent is reactive. It must respond to changes in the environment in a timely manner. It is autonomous. The definition of autonomy is quite tricky, but I'm going to go with can control its own behavior. It's proactive. And this one's even as tricky. I'm going to go with exhibits goal-oriented behavior. And the last one we don't require, but we put it up there anyway, communicating. So maybe this agent communicates with other agents. So your human does all of these things, one is presuming. I reckon my dog exhibits goal-oriented behavior. It seems to come up to me, give me a stupid look, walk down the stairs, go into the laundry are where the treats are stored. It's hard for me not to conclude that the dog does not have goal-oriented behavior in that it wants a treat, because it somehow leads me to the laundry. We have to be extremely careful, and this is part of the lesson of this lecture, in ascribing such goals to the dog. The dog does not know what the laundry is. The dog knows that there are treats in there and can sort of navigate through the house and get me to where the treats are, but it doesn't know or have a goal of going to the laundry, even though when we described it, or as I just described it to you, it wanted to go to the laundry. That's my language, not the dog language. Let me give you another example. Sea creatures. So this is the minimal self-control. So perhaps I'm drawing the line about here. So there are some sea creatures that when they require energy, I think this is how it goes, they have the equivalent of solar panels or something. So they actually float to the surface and get sunlight that is shining onto the sea. So those things seem to, well, maybe, exhibit goal-oriented behavior. They're reactive. They only go there when there's sunlight. They seem to be doing it themselves. It's not that somehow the currents take them up there. And it seems to be goal-oriented in that they get food or energy from the sunlight. Thermostats, no. So what's wrong with thermostats is that they have a representation of the current temperature in the room, and that representation is the length, let's say it's the length of a piece of metal. The thermostat doesn't believe that the room is too cold or too hot. In fact, the length of the piece of metal is an indicator of the temperature in the room. It indicates, but not perfectly, or maybe perfectly, the temperature in the room. And that indication sort of only works because of the way thermostats are designed. But there's no real goal-oriented behavior. It's a bit hard to say, well, the thermostat wanted to turn the heating up or down. And so that's the problem with the lamp as well. So when we think about our current robots, that's a kind of spectrum, and where do they sort of sit on the spectrum? Hopefully they're somewhere in the middle, but not necessarily. Now I'm going to tell you about frogs. I've got a video about frogs. So this is the importance of situatedness. There's a famous paper called What the Frog's Eye Tells the Frog's Brain. And I was surprised to find that McCulloch and Pitts were both the authors on that. So I thought they were, but 1940. So let's have a look at this little frog doing its thing. If it's working. Is it doing something? There you go. Frog caught the fly. Well, okay, didn't see that. I didn't watch it to the end before. Anyway, you might have realized there the frog was pretty fast. Very fast, in fact. So we might say the frog knew there was a fly in front of it. This is the indicator example. I got it wrong. Actually, the frog does not respond only to flies. And with this being YouTube, it's so annoying. But the correct story is that there's a black dot. If you put a black dot in front of a fly, it will actually stick out its tongue to the black dot. And there was, when I did this yesterday, there was some guy who had written an app. The app shows a picture of the fly, and the frog, at a certain time, licks the app, basically, licks the iPhone. I can't find it at the moment, but maybe you can find it. So, in this case, this is the indicator. The black dot indicates the fly. So the question is, does the frog know there's a fly there? The frog will try to catch anything that's a black dot that comes into its field of vision. So McCulloch and Pitts sort of looked at the actual vision system of the frog and were able to determine this somehow in 1940. So that's the first point. It's not a perfect indicator of a fly, but it is in the frog's environment. So there are no black dots in the lily pond where the frog lives most of the time, in fact, all of the time. So there's some theories that say, even though the black dot indicates, but not perfectly, the presence of a fly, nevertheless, the frog knows that there is a fly there when there is a fly there. Because in the environment in which the frog operates, there are no black dots, only flies. So the implication for the design of an agent is we do not need a fly detector for this frog. It suffices to have a black dot detector. A black dot detector will work 99.99999% of the time in the lily pond, maybe 100% of the time. And if it doesn't work, it hasn't cost the frog anything, maybe just sticking its tongue out a few times, hasn't really cost it very much in terms of energy, but saved it a lot in terms of effort, because the frog has a pretty small brain and doesn't really need a fly detector. It only needs a black dot detector, something like that. So the point we're making is that the frog is situated in this environment in the same way that a robot, say like an autonomous car, self-driving car, only operates on the road. You take that car out of the road, it's going to have a lot of trouble. So here, the frog operates in the environment under which its mechanisms work, and work adequately, and have been designed that way by evolution to work that way. So evolution got the frog to where it was by just having a black dot detector. It does not need a fly detector. Nevertheless, we might want to say that the frog knows there's a fly in front of it. Certainly looks like that. So the question that poses is, how do people differ from frogs? No one really knows the answer to that one. So we're sort of, how much of people's reasoning is situated in this way, that we don't really, we're sort of taking shortcuts all the time, shortcuts that are somehow adequate for the tasks that are needed to be performed. So when you come to design a robot, you do not need to, what we would say, if I was talking about software engineering, we would say, do not over-engineer the robot. So you don't need to put a whole lot of effort into designing the fly detector when the black dot detector will work. And RoboCup is a bit like that. And I forgot to tell you, but this is my prompt. RoboCup is in Sydney in July. It would have been in the mid-semester break, but of course now it's in week something of term. And Claude Samet, who's running the RoboCup, would like volunteers to come along and just help out for one session. So the RoboCup is huge. It takes up the whole of the ground floor of the convention centre in Sydney and half of the upper floor. And you have these little robots. I've only been to the RoboCup once, and it's incredibly noisy because these little devices clackety clack, clack, clack all the time. But again, we have this sort of problem. Maybe it's a problem. How far is RoboCup from real robotics? Well, there's the equivalent of the black dot. Right there, that's the orange ball. So does the robot know that it's got a ball in front of it? Well, only if it's on the RoboCup field and we're playing by the rules. Usually the first problem when you set up in a new environment for the RoboCup is training the vision algorithm to detect the right shade of orange, because somehow lighting is different from one room to another and it doesn't actually work as well. There are many other problems, no doubt, but that's one of them. Anyhow, so if people want to volunteer, Claude will be very grateful. I think it's July the 5th to the 8th in Darling Harbour. So just go along for one session, they'll be grateful, because what happens is the rules sometimes allow you to pick up the robot. So depending on which game you're playing, sometimes the robots, they have these two-legged robots that would fall over and they couldn't get up again. So the rules allowed you to come on the field and pick them up. These are the old-fashioned four-legged robots. So my point is the robots are a little bit like the frog in that sense. They only need to work in the domain for which they are designed. And they make it a bit easy for you by having the orange ball. Easier. So to specify an agent, so we're going to look at maybe this a little more in the tutorials, but you have these percepts or perceptual aspects or elements, inputs to the agent from sensors, and actions that are the outputs available to the agent. So a set of possible actions, not just further we're going to specify what happens when, and goals. So these are the possible goals, objectives or performance measures. So there's an idea of metrics here as well. How well is the agent performing? So your performance metric for the frog could be how many flies you caught in the last week or something like that. And the environment is the world in which the agent operates, so always constrained in some way. So basically, what you have to specify when you implement or design an agent is a function that takes all the perceptions and turns them into actions. And perception, as we already said, was a little bit hard. So Russell and Norvig take this idea of the ideally rational agent. Stuart Russell worked on this a little bit himself. Indeed, there's a kind of utility, the idea that the ideally rational agent somehow acts in order to maximize the expected outcome of some performance measure. So as I hinted at before, the agent does not have to know what the performance measure actually is. So the frog doesn't have to know that its task is to eat flies. We know, or somehow evolution knows, that that's the performance measure we apply to the frog. And for RoboCup, it's pretty simple. The performance measure is, the ultimate performance measure is winning the game, but this expected maximize, it's expected utility theory. So there's utility of outcomes, so the agent gets rewards. It's assumed that these rewards are known, and the performance measure measures those rewards, and the agent's supposed to act in order to maximize the expected. So there's a probabilistic aspect here. The expected reward may not always get the expected reward, but that's the idea. Well, that is a nice idea, but it doesn't work because one reason it doesn't work is that agents in reality are resource bounded. So the whole point of having or discussing agents is that agents cannot make those decisions. So, for example, if it was a chess game, I'm going to look at chess in a minute anyway, so maybe I'll defer it. But if it was a chess game, you don't know or can't compute what the best move is. So a resource-bounded agent has to make good enough decisions based on the perceptual, computational, and memory limitations. So it's a bit like the frog again. It doesn't have to really make sure this is a fly before going for it. Say, well, black dot, good enough for me. There's an efficiency there that it can be faster. So the point is it could be faster if it just goes for black dots, and at the cost of potentially being wrong. But if it aimed for the fly detector, it would be too slow and wouldn't catch any flies, because by the time it recognized the fly has gone past. So there's a sense, the technical word is attunement. So I didn't put that in the history, but the agent is attuned to the environment and takes advantage of that in order to sort of steer a path and so make some design trade-offs in order to achieve these objectives, even though it won't be perfect. So Russell and Norvig look at a few examples, and I'm not really going to go through this because this is the less interesting part for me, but I guess the idea is it's useful to think about what sort of, if we're building a system, what sort of inputs that system has, and that's what these percepts are. Percept just comes from perception. So what are the inputs? So there's meant to be a cycle. So the agent's getting an input and every time click, and then making an action every time click. So it's very much a dynamic kind of system. So you think of the automated taxi driver, now we call it self-driving car or something, so it's going to get inputs from its cameras, the speed, GPS, whatever, and the actions are quite simple. It's either going to steer or it's going to accelerate, brake, or whatever. There might be some goals. Now, we take this with a grain of salt. This is just sort of a tool for thinking about how to design the things rather than the actual detail being correct on this slide. So there are some goals which, remember, relate to this performance measure that maybe the agent doesn't even know about. And then in the environment, well, it's got to be a little more than that. It's got to be the actual properties of the environment that make this agent work and that are utilized, so that you are utilizing into your design trade-off. So it actually constrains the agent in some way. So the idea of the trick is to somehow get this agent sophisticated enough, yet constrained enough to make it work. So it wouldn't be a very good idea to build a sort of self-driving car that could drive anywhere. It's much more sensible to build a self-driving car that can drive on a road whether you've got markings on the road, you've got signs up there on the road, you've got traffic lights and things like that. And you've got to take advantage of all of those things. So that's the sort of things to think about when designing an agent. So an agent itself, in our sense, consists of, it has an architecture and a program. So here's where Russell and Norvig don't quite get it right either. The architecture refers to all the hardware, the bits, and the software components as well. So not just, it's not an arbitrary program, it's a program that exists with some software elements. And the organization of those elements is very important. So the architecture actually constrains what you can do, actually constrains it. The program then must map the inputs to the outputs, where the inputs are the perception we've had so far, and must produce an output. This is the most very general sense. Now, of course, the agent itself doesn't have to remember anything about its prior history. So the frog maybe doesn't remember at all anything about its history. But the robotic and the self-driving car may not remember much either. It might just remember the speed it was going before. Maybe it remembers whether it saw a traffic light in the previous cycle. Things like that. So you don't have to remember everything. We don't want to incur the cost of memory. So the trick is, what sort of memory do we need? What sort of architecture do we need to build a reasonable agent? So someone was asking me in the break about, why don't we just use search, brute force search? Well, the answer is because these agents are resource boundedness, and so representation is also important. So here are three sorts of representations. This does come from Poole and Mackworth, that you could use for, let's say, chess. Now, chess, maybe not an agent, but let's pretend it is for the moment. So by one estimation, there are 2 to the power of 43 distinct states in the game of chess. Maybe there's more, maybe there's less, doesn't really matter. There's a lot of them. So just by state, we mean essentially a number. The state has no particular structure. You're in state 252. What do you do? You're in state 375. What do you do? So implementing the chess-playing agent like that is going to be very difficult, because the state has no particular structure, and if you learn something about what to do in state 252, that wouldn't tell you anything at all about what to do in other similar states. So the other thing is, of course, if we wanted to maximize performance, where we wanted to make the best move, whatever that was, one that hopefully led us towards winning the game, it would take a long time. So, if all we have is just the state, the number of the state, we don't really know much about this game tree. So we can't. So doing search on a system like this with a large number of states is not going to work. So sometimes states can have features. So the feature is a basic thing, like there might be a number of features, maybe 100 features, which could have potential values, let's say 1 and 0. And so our state could have a feature F, let's say if there's a passed pawn. So we might have a lot of features, and we'll look at the chess board and say, okay, that's got feature F, it's got feature G, H, and so on. And then we know how to play based on that. So the features abstract from the states, basically. And then a more complex representation might be some logical structure. So the state might say, okay, this one's got a queen in the first row. This one's got queen attacking rook, or something like that. So the state itself now has propositional type of structure, things that can be true or false. And then the agent's program will work on the states. So the point is, these representations now play a role in terms of how the agent program decides what action to perform. So so typical machine learning thing will look at features, or typical planning system might look at propositions. And that's the point of Poole and Mackworth, that there's different methods to work with different representations inside the agent. And it's up to you, or the designer, or evolution, to say what the good representation is. So it may be that you can come up with a really good chess player by using states, but I don't think so. And you probably need a bit more sophisticated structure in your representation than that. So, as Poole and Mackworth say, the representation you choose has to be rich enough to express the knowledge needed. Now, this is knowledge at a very abstract level, not the agent really needs to know, but the agent has some knowledge that's needed to solve the problem, or we characterize it as having this knowledge to solve the problem, and the representation has to express that. Ideally, be as close to the problem as possible. So the representation should be compact. Well, I don't know what natural means, maintainable. The key thing to me is efficient computation. So the representation has to identify what's important about this problem. So if you're doing the self-driving car, it's got to identify people on the street. You don't want to run them over. And it's got to be able to trade off accuracy and computation time. So that's what I was saying before. The trade-off is very, very important. So no agent's going to be perfect because it's got to operate in this limited environment and be resource bounded. So in terms of the programs, Russell and Norvig put it like this. So there's a class of agents that we might call reactive, purely reactive agent. They call them reflex, but the correct term I think is reactive. This agent has no memory whatsoever. So it just looks at the state of the world now and does an action. So one way to do that, they say the way, but you can have simple condition action rules. If the condition is this, or if I'm looking at, I don't know, something, then I do this particular action. And I don't remember at all where I've been before. So this simplest sort of reactive agent has no memory and no future reasoning, no planning at all. But surprisingly, these some reactive agents can do very well in some domains. If your perception is good enough, for example, you don't need a memory, so we'll say. On the other hand, you may need an agent which has this internal state, so maybe these are features. And this time, I guess there are various options. I haven't really looked at what Russell and Norvig said that much, but looks like there's a kind of sense of, okay, looks like it's sort of predicting which actions are going to lead me to somewhere. And so I can have simple rules again, but I need to know what are the outcomes of my actions. The goal-based agent actually tries to achieve its goals by working out a sequence of actions. So it tries to predict more than one step into the future. So this is where some of the more sophisticated search and planning algorithms that come in. And the utility-based agent, this is a Stuart Russell special again, this is one that has its performance measure explicit and conducts preferences. So the agent itself will decide or calculate its expected utility of doing certain action and then go away and actually do that action. That again, so as we've gone up the hierarchy here, we need more computation power. So the simplest one, the reactive agent, is not necessarily a bad thing. That's the whole point of this discussion. It may be that for the environment and for the task this agent's supposed to do, the reactive agent is sufficient. In such a case, you build a reactive agent. So these RoboCup, going back to the RoboCup soccer, when I first went to RoboCup, which was a long time ago, basically any robot that could kick the ball was a big win. You know, because some teams couldn't even kick the ball. So if you just randomly managed to kick the ball, some time or other it would go into those goals and you would get a point. And that was the team that won, sort of thing. Now, it's a bit more complicated now, but you don't necessarily care. Maybe, what do you need to do? You maybe just need to remember where you saw the ball before, or you just don't do anything. You just wait around until the ball occurs in front of you, then kick it. So that's a strategy that you can adopt. And as I'm saying, 20 years ago, that might have won you the tournament. You don't have to worry about passing the ball to anybody else. You don't have to worry about kicking it towards the goal because that's too hard. Just kick the ball. Recognize the orange blob and kick it, and that's enough. So that would be a purely reactive agent, and it might perform quite well in that environment. Now, I mean, other agents that are more sophisticated might try to pass the ball to their their teammates or try to direct the ball towards the goal, the soccer goal that is, and that might require some more computation time. So we'd have to work out where the goalposts were, for example. So then the reactive agent doesn't care, doesn't have to orient itself on the field. But the slightly more sophisticated agent does need to know where it is in relation to the field or in relation to the other agents. So it's got to have a much more sophisticated vision system as well. So in general, as we're going up the hierarchy, the agents get more complicated, but therefore they are slower to react because they've got to do more computation. So another thing to look at is the types of environment. So Russell and Norvig make a big deal of this. I don't know that they need to make such a big deal of it, but well, let's try anyway. So you can think of certain environments. So I guess the point is, don't just consider the agent. You've got to consider the environment in which it's operating. So some environments are fully observable, some are partially observable. There's a whole, and the reason that's so important is there's a whole theory of partially observable Markov decision processes that we'll come to maybe in weeks 6 or 7. So does the agent's sensors give you access to the complete relevant state of the environment? Maybe I should have put the word relevant in there. So if you can get all the information from your sensors, you don't need to remember anything. If that would be fully observable. Whereas if that's not the case, then clearly you need some memory. And then we have some more interesting ones. So is the environment itself deterministic or stochastic? So deterministic means if I do some action, or maybe if I try to do some action, I'm not sure, will the outcome be determined by just that choice? So, or not. So looking at your RoboCup again, typically these things will be stochastic, and there's a statistical set of outcomes, distribution over outcomes. So if you kick the ball, the agent cannot really choose to kick the ball into the goal. It can only choose to kick the ball. Where the ball ends up is not determined by just that agent's, a choice, determined by many things. But perhaps from the agent's point of view, there's no way of predicting where the ball's going to end up. So if the environment's like that, from the agent's point of view, that you can't tell what's going to happen, then the agent has to take account of that uncertainty in its reasoning and in its choice of action. So that's where reasoning about uncertainty comes into the course. So, as I said, Stuart Russell does a lot of work on reasoning with uncertainty, and machine learning deals with uncertainty as well. Certain planning domains you can assume to be deterministic for the purposes of our design. And then there's this question of the timing. I guess it's the timing that's important. Can you just deal with one event as it happens? And can you, once you've dealt with an event, forget about it? So if so, the thing is episodic. You don't need to plan ahead. If that's not the case, so in other words, it could be, you could design your agent to do this, but I think if it was RoboCup, you just decide what to do each time. You don't pay attention to sequences of actions. So you don't need to plan ahead. You don't need to sort of come up with a sequence where you might first do A, then do B, then do C, and then kick the goal. So if the behavior if the environment is such that the thing is episodic, then you don't need to plan, apparently. So static versus dynamic. Now this one, I'm not really happy with Russell and Norvig's description of it, but you can see what's going on. How dynamic is the environment? If the environment changes while the agent is deliberating, there's a big problem. So suppose we're playing our robot soccer, and then an orange ball appears in front of me, and I think about what I'm going to do. In the meantime, somebody else takes the ball away or kicks it. Then I didn't get to execute my action. So in a dynamic environment, according to them, every environment is dynamic, but in this sort of dynamic environment, while you're deliberating, the environment changed. So the action that you chose to perform will no longer be impossible, maybe, or no longer relevant, because essentially your thinking is too slow. So some of my colleagues work with the Air Force, and they're very interested in fast-moving fighter pilots. So they train the pilots. So they have to be pretty fast. So a bit like that frog who has to respond to the fly, you have to respond and make your actions in a very, very tight time frame. If you have to pay attention. So if you're the agent, you haven't got time to think. So it goes back to this computation with chess again. Chess does have time limits, and if you don't make your move in the relevant time frame, then you're not going to be able to play the game. And then the other thing that we draw upon is this discrete versus continuous. So I suppose this, again, abstraction level, can a typical vision system might produce some kind of continuous set of numbers, I suppose. It could be the value of some feature, maybe the temperature or the quality of the light or something. I'm not really sure what we have in mind here. Or maybe there's if you're a robot, you've got wheels, you're moving around the world continuously, that might be continuous action. Whereas discrete actions is you might take one step at a time. So these considerations all, which are, about the environment, but also about how the agent works and lives in that environment, dictate features of the design. So I'm going to show you something more concrete now, having talked about that in sort of abstract terms for quite a while. So this is the layered architecture. So finally we get back to what the textbook actually says, which is good, which is, it's not so simple that we always have just a reactive architecture or utility-based thing, but the typical robot these days probably has a layered architecture. So by a layered architecture, I mean it's got a hierarchical decomposition of controllers. So a controller is something that, a bit like what we just called an agent before, it gets percepts and actions and sends commands. But if you're a high-level controller, you get your percepts not from the environment, but from the lower-level controller below you, and you send your commands to the lower layer below you. So there's this, the point is that the higher-level controllers can be slower. So the controllers operate at different time scales and have different representations. So your low-level controller is probably some very simple or comparatively simple mechanism directly connecting the percepts to the actions that sort of keep the robot moving. So if the job was me trying to walk out the door, I've got some low-level controller that sort of just keeps me walking in that right direction and gets me to the door. But the higher-level controller is the one that made the decision go to the door as opposed to go to that door, for example. And so the higher-level controller tells the lower-level controller, get the body to that door. And, of course, I have to avoid those chairs and this desk. So the controllers may operate at have different representations and at different time scales. And the most important thing of all, I think the textbook doesn't quite mention this, the lower-level controller can override its commands. So it's not strictly hierarchical in that always the brain or whatever is telling the body what to do. Sometimes the body says, well, look, sorry, you're going to run into the chair. I'm avoiding the chair. I know you told me you were going to get to the door, but too bad, I'm avoiding that obstacle. So typically, if the high-level controller over-specifies, the lower-level controller overrides. So this is the kind of design that is used for robots that are exploring robots, so robots on the surface of Mars that have missions that they might have to go and collect some rocks, but they also have to avoid getting stuck into craters and things like that. So lower-level controllers move the robot around and keep it steady from toppling over. Higher-level controllers say, go and get me some rocks, or maybe even work out where to get the rocks, or maybe even if there's a battery, has to work out where to get more power for its battery, and things like that. So the higher-level controller tries to have longer-term view of the future, whereas the lower-level controller has to sort of has a simpler task, but has to be more reactive in time. So that's the kind of layered architecture that you might do. Not in this course, because we're not going to look at robotics, but if you were to build a robot, you would certainly be thinking about layering the architecture. So this is the textbook version of the layered architecture they use for this so-called delivery robot. And I don't know if they really built this thing, but there are plenty of delivery robots around. So the one in, let's say, Amazon warehouse is a bit like this, if they have them. So there's some low-level controller which has to steer the robot, report the obstacles, and just maintain its position. This secondary layer, well, whatever, it says decides which targets. And this one decides on a target and avoids the obstacles. Okay, so there's even a lower level layer than the one I said before, which just keeps the robot moving. And the higher level robot is the one that specifies the plan. So in this sort of diagram, the actions flow downwards and the perceptions flow upwards. But it's not really, remember, there's some actual computation here. So at this level, the robot has a whisker, what they're calling it, a little sensor. So the whisker presumably runs a little current when it touches an obstacle. Whisker touching an obstacle is not something that the second layer understands. Whisker, voltage equals 1 is not something the second layer understands. That has to be translated into something like obstacle. So the second layer has its own language and talks about obstacles. This one, maybe the example's not, maybe my description of the example or the example's not right, but there can be stuff down here that maybe doesn't talk about obstacles. So maybe obstacles only get to be a concept, as it were, in the upper layers. And the top level layer might talk about users. This user has ordered a book, so we're going to get this book. But the lower layer hasn't got any clue about books. It just reaches out and grabs the thing on the shelf, whether it's a book, coffee cup, or whatever. So that's the layers, the layering thing. So in terms of the example, this is in the textbook as well now, this is how they've, don't worry too much about the notation, but the main thing is how they've characterized the behavior of the middle layer. And the middle layer, I didn't really look at this. It takes a timeout and a target position. Essentially, from above, it takes its goals from above, it takes its perceptions from below, and works out which action it's going to suggest. So, and it will compute a new target position, so it may update. So we haven't really talked about updating yet, but we will. So if the agent has an internal state, of course, it should observe the effects of its actions. So the new state that it goes to might depend upon what the next set of percepts is. So if you're playing the robot soccer, for example, and you kick the orange ball, then the next layer, the next state you're in, may be dependent upon what you observe. So you will observe where that ball was kicked. And then you'll need to update your state. So, your memory can be wrong. If you happen, so for an example there might be, you thought the ball was there, but actually it's over there. If the perceptions don't allow you to correctly update and maintain your state. I don't think that's a characteristic of this particular problem. And then just for fun, we gave you the actual code to show you that it really exists. So there's very simple. So the idea again, I suppose, and this is Poole and Mackworth again, it fits on a slide. Surprise, surprise. Essentially, there's a very simple little loop again that says, while we haven't arrived at where we're going, and there's the timeout still proceeding, basically, oops, this way. Basically, we either steer to the left, we steer to the right, or we just whatever. So it's very simple, and the aim is, of course, to have very simple programs at each of these levels. We don't want to have complex decision making because the decision has to be made in the relevant time frame. Okay, so the top layer again is even more abstract. This one just remembers a list of target positions. So it remembers, so if you were buying the books from the warehouse, it says first get that one, then get that one, then get that one. So the second layer might plan exactly how to get from A to B. This one just says, get these things in sequence, and tells the lower layer to do that. Okay, and then this one has, again, a little timeout. So it's a very simple little loop. So now we've got the problem of coordinating, or synchronizing is the word I'm looking for, those layers. So that of course, each of the layers works at a different time scale. I don't know how they handle this in the textbook, but in theory, the lower layer is getting a lot faster reaction time than the upper layers. So maybe those percepts come in at the relevant speed, but the problem is the upper layers cannot process them fast enough. So in a certain type of environment, that could be bad. In a fairly not a fairly safe environment like a warehouse, probably not going to cause you a problem. But you do want to, these robots zip along pretty quickly actually. So you don't want them running into one another. So maybe it is useful to somehow coordinate these robots. So if there was any coordination, that might happen at the top layer as well. So I guess the other point to make about this example was this decision for the middle layer. I didn't really read the code much, but essentially it's most of the time we go, if you're seeing the whisker, in other words, if there's an obstacle, just turn left. So essentially it's just that. If you can go straight ahead, otherwise turn right, or something like that, or turn in the direction of the object. So it's very simple avoidance, essentially, turn left. But it works. So the point is it does work. So if this green thing was the obstacle, the very simple reactive rule that says always turn left if there's an obstacle does the job. So it will hit this green thing, the whisker will come on, it will just turn left. Oh, now I can go straight. I can go straight. Oh, now I can go towards the goal. And there we go towards the goal. So the purple things are presumably what the top layer says the goals are. So the point is that these simple reactive rules can actually produce, dare we say it, intelligent behavior, but intelligent looking behavior, even though there's no real planning. So there's no one who said, oh, for me, you need to know where this obstacle is. You need to plan. You need to work out how you're going to get around this obstacle. In fact, that doesn't happen. That's exactly what doesn't happen. What happens is the robot starts on its journey, comes up with an obstacle, decides, I'll turn left, turns left, just keeps going. Then when it gets to the end of the obstacle, goes straight ahead. So that's going to work sometimes. And maybe it works all the time. But whether it works depends on the environment. So that's the key point again. It's this, if we have control, or if you were the designer, if you were the designer of the warehouse, you would have control over the environment, then clearly you could design it in such a way that this agent worked. But if we were, trickier, we could set it up probably in such a way that we could box this little guy in. Maybe we could make it such that this method would fail. So this will only work some of the time, and it works in this particular case. But whether it works depends on this property of the environment. And so again, this is the Rodney Brooks point. You don't need a complex planner to do this obstacle avoidance. The agent will somehow manage to achieve its goal with very simple rules, operating dynamically in time. And this one has some advantages as well, because if the obstacles move around, then the agent will also be able to cope with that. So the problem with the planner, who plans everything in advance, is that the world can change, as we said before. If the world changes while we're doing our planning, or after we've done our plan, then our plan becomes potentially useless. And so it's actually more useful to the agent to dynamically respond to these obstacles as they appear, rather than to develop a plan in advance of how to deal with the obstacles, because the obstacles might appear during the execution of the plan. So there's this interleaving of planning and execution that's characteristic of these agents. Absolutely characteristic. So your traditional AI work talks about planning in a disembodied sense, which is we got all the information, or as much information as we have, and we develop our plan. And that kind of thing can work. So if you're planning a holiday or something, you typically try to get as much information as you can before you go. But then in these dynamic environments, that, like RoboCup soccer again, the obstacles can appear. So if the obstacles were the other robots, there's no possible way you can predict where, well, very difficult to predict where these other obstacles are going to be. If you want to avoid another robot, or you want to get to the ball, if that ball's behind another robot, for example. So again, simple mechanisms can work, but the reality, I suppose, in terms of our architectures is that the layered approach seems to be the one that best handles this mixture of being reactive but also being proactive, having goals and responding to goals. So that brings me to the sort of last topic, which is, before I show you some Python anyway, maybe. So these belief, desire, intention agents. So these are agents that are probably more complex, the most complex sorts of agents that have been developed. But they, again, are constrained in a particular way. So first, let me give you the Bratman version, and then I'll tell you what has actually been implemented. So the idea is, how can some agent have, be more complex than the ones that have just these reactive rules? So, in other words, have a little more like human psychology, have beliefs or goals and intentions. Well, what are beliefs, goals, and intentions is the question that Bratman set himself to answer. Well, we sort of knew what beliefs and goals were, but intentions was his particular interest in this book. So a belief is then some propositional representation of some fact about the world. So it might be, the ball is in front of agent 2 or something, is a proposition. Desires are preferred states of the environment. So my dog's desire was to have a treat, something like that. Desires can be inconsistent. So desires can be, you have a desire to lose weight, you have a desire to eat chocolate cake. You know these things are inconsistent, but that's okay for desires. Goals, on the other hand, are rationally chosen, this is according to the theory, rationally chosen desires that the agent is currently pursuing and have to be consistent. So in other words, goals have to be reasoned about. In the same manner, I just had those desires. I couldn't have the goal of losing weight and eating too much chocolate, because that would be inconsistent. Assume that I know that's inconsistent. So the agent has to achieve certain goals, so that's the sort of traditional planning sort of agent, and intentions. So your standard utility or decision theory agent, according to Russell Norvig, calculates a decision tree and says, okay, let me just choose the path on that decision tree that gives myself the maximum expected utility. So it's assumed that at the end of each branch in the tree I get a reward, and I know what that reward is. I know a probability distribution over all of the branches all of the time. I can calculate the expected reward from any given action at any given time. So that's the classical decision theory approach. It would be like saying the way to play chess was to calculate the entire game tree for chess and then pick the best move. Well, we can't do that. For a start, you can't actually calculate 2 to the power of 43 states or represent those on a machine, let alone calculate the probability distributions. Nevertheless, something like that is what AlphaGo does, I think. It sort of calculates for some amount of time into the future the expected utilities of moving in certain places. But generally, you can't really do that. And so that's the reason that intelligent agents, or rational agents, according to Bratman, have these intentions. So intentions are things the agent has chosen to do and committed to. So you keep your intentions from previous time points. You don't revise them all the time. Intentions are things that pose problems for planning. So your intention, you might choose a goal, and my goal might be, let's say, I don't know, what's your goal? To graduate, getting your master's degree or undergrad degree? So that goal might suggest to you certain intentions that you need to adopt. And those intentions then constrain your further choices, so they are compatible with the existing intentions. Intentions, of course, also operate at different timescales. And intentions, importantly, lead to action. So for Bratman, intentions play these three roles, and they are all defined functionally. So there's no mystery. There's no mysterious thing that intention has to have. If there's some sort of representational mental thing that does that, then it's an intention. And the agent, therefore, is viewed as maintaining a set of commitments and acting on those commitments. And furthermore, although I didn't have it here, I don't know how I got that one missed out, but intentions also are very important for coordination. So the example is one, suppose your wife and you have the car keys, and you have to give the car key to the wife or something at a certain time. You have to coordinate that activity. So that constrains what you can do in order to fulfill your commitments to other people. So sometimes we've mostly in this lecture talked about agents just themselves acting individually, but there's also this coordination aspect to agents that Bratman does talk about as in more detail, but it's not really part of the definition of intention. So what's been done in terms of the AI literature is to try to implement something that looks like this. So take this one with a grain of salt now, in that there's a cycle, and events come into this cycle, and the events trigger options. So the agent has to be opportunistic. So the agent has to balance the commitment to its prior intentions with these new opportunities that arise in the environment. So the new events, the things that are observed, these are like the percepts, trigger these options in a straightforward way, but the options are plans. So the options are plans, and these then become candidate intentions. The events also cause revision of beliefs. So the beliefs are usually expressed in some explicit form, in explicit language. And then there's a deliberation element. So the deliberation is pretty quick, because this is one single time cycle. The deliberation says, which of my intentions am I going to pursue right now? So typically, if one has several intentions, there's not in this system any way of determining whether these intentions interfere with each other. That's a whole other problem. But you might just pick the intention you chose last time. So if my intention was to get back to my office, I'd keep doing that for a while. If I had some other intention, which is to maybe fix up some of the errors on the slides that I noticed, well, I'll do that, but I'll do that later. I'm not going to interleave these intentions. Going back to the fighter pilots, this is the thing they use. So you have to make a very quick decision as to, do you basically continue with the intention that you had previously, which is what you want to do, or should you turn right or avoid this other aircraft that seems to be approaching in your direction? So this is the kind of deliberation. It's not really deliberation. It's not how do I choose to achieve my goal. It's rather which of the intentions that I've sort of taken out of this plan library. So there's a preset series of plans. Apparently pilots have this as well. So there's only a certain number of maneuvers you can make. And when you deliberate, you're saying, which maneuver am I going to take? You haven't got time to replan your maneuvers, certainly if other people are relying on you acting in that way. So this sort of architecture has a very tight loop. It looks like this. So it has some loop that says we generate some options from our event queue. We choose some of those options. We maybe update some of the intentions in the sense of, well, maybe some of those intentions are no longer feasible. Maybe I've actually achieved some of them. So that's good. Achieved the goal of some of them. Then I do one action, and then I observe what happened. So this is a very simple cycle, but it works, and it works in some environments. So that's the whole point of the lecture again, that this is useful sometimes. Now, there's a problem that I didn't mention. So these are 4 things, but I forgot the 5th thing. So this is useful in very dynamic environments where you've obviously got to be able to formulate plans in advance. So the agent chooses a plan and then executes it. it's good to have continuity of commitment. So you want to keep doing the same thing as long as you can. The agent needs to respond rapidly to any changes in the environment, and its resources are limited. The bad side, and the thing I should have written down, is where the events aren't too fast. So basically this will fail if you can't process the events fast enough. So if the world is so dynamic that this cycle is too slow, then you're in serious trouble. You'll be acting on the event. Typically these things, there's two ways to do it. So you either put the events in an event queue, which is what we said before. Well, I didn't say, but that's what it says here. So that would mean we have a queue of all these events that I previously observed, and I'm taking them off the queue one by one and processing them. If I fall behind in time, then I'll be acting upon what I observed several time cycles ago. So the world might have changed. The new percepts might have overridden the old ones that I'm acting on. So if this event queue gets too long, then I won't be able to ever catch up. So that's a serious problem, or potentially a serious problem. That's one way to do an event queue. The other way to do an event queue is to say, if I didn't process the event, throw it away. Just take the latest one that I've seen. And the problem with that, obviously, is I'm going to throw away stuff that's useful to observe. I may not be acting appropriately either. So this one is also very much about timing. So you have to be able to execute this loop in sufficient time frame for the agent to act. So what my point, I suppose, and this is the toughest lecture to give, so from now on it'll be easy. Yeah, easier, I think. So the next lectures will all be technical, but this one's about what AI is and how to design an agent. So the summary I'm making here is that assumptions about the environment dictate the nature of the agent. So the capabilities that you only need to design the agent to work in the environment in which it is situated. It doesn't need to be over-engineered to handle more complex scenarios. So you're never going to get the perfect general agent. You know, it's very, very useful to develop these general purpose agents that work in constrained environments, and to exploit that constraint. So you think of the agent plus its environment as like a coupled system. So, for example, the driverless cars operate only on standard traffic conditions. Maybe we can make that more general, but maybe not. Specific architectures, therefore, constrain what the agent can do, but also in a good way, they become more efficient. And we already saw efficiency is very important for getting agents to perform properly. Before I finish, let me show you one thing more. So I wanted to show you, I don't know if people had done, in 9021 had done the used Spider. So Spider is a sort of IDE for Python. And so in the first tutorial, we're going to give you this very simple agent that essentially goes around the grid world, the little world of grids, and collects food. So I want to show you some actual Python code. So this agent sort of has a cycle, and it sort of looks whether food was seen previously and updates its list of food. It's a pretty stupid design in some respects, and so part of the exercise is to fix it. So I don't know if you use Spider, but if you just hit this little play button here, it'll actually run the agent and spit out some code. So what I'm suggesting, we won't do it now necessarily, but that's already there on the web.